All right, so starting with number 12, so there's only one critical point. It is at x is 1/2, and it is the location of a local maximum because y prime changes from positive to negative at x is equal to 1/2. Number 13, there are two critical points. At x equals 0, the function has a local minimum because y prime changes from negative to positive at x equals 0. And at x equals 2, there's a local maximum because y prime changes from positive to negative at x equals 2. Number 14, there are three critical points. At x equals negative square root of 6/5, there's a local maximum because y prime changes from positive to negative at x equals negative square root of 6/5. At 0,
sorry.
Hello.
We got caught up in the line.
At 0, there was neither because y prime does not change sign at x equals 0. And at x equals the square root of 6/5, there's a local minimum because y prime changes from negative to positive at x equals the square root of 6/5. For number 15, there are two critical points, x equals 0 and x equals 1. X equals 0 is not a critical point because the original function doesn't exist at 0 either. At x equals 1, you have a local minimum because y prime changes from negative to positive at x equals 1. For number 16, at x equals negative 3 over the square root of 2, there's a local minimum because y prime changes from negative to positive at x equals negative 3 over the square root of 2. And at x equals 3 over the square root of 2, there's a local maximum because y prime changes from positive to negative at that point. Number 17, at x equals negative 1, there's a local minimum because y prime changes from negative to positive at x equals negative 1. And at x equals 1, there's a local maximum because y prime changes from positive to negative at x equals 1. Then for number 18, f is increasing on the closed interval from negative 3 to negative 2, and again on the closed interval from 0 to 2, because f prime is greater than 0 on the open interval from negative 3 to negative 2, and again on the open interval from 0 to 2. F is decreasing on the closed interval from negative 2 to 0, and again on the closed interval from 2 to 3, because f prime is less than 0 on the open interval from negative 2 to 0, and on the open interval from 2 to 3. At x equals negative 2, f prime changes from positive to negative, so we have a local maximum of f. At x equals 0, we have a local minimum of f because f prime changes from negative to positive. And at x equals 2, we have a local maximum because f prime changes from positive to negative. For number 19, the function is increasing on the closed interval from negative 2 to 2. There's not a break at 0 there, because f prime is greater than 0 on the closed interval from the open interval from negative 2 to 0 and the open interval from 0 to 2. F is decreasing on the closed interval from negative 3 to negative 2 and from 2 to 3 because f prime is less than 0 on the open interval from negative 3 to negative 2 and the open interval from 2 to 3. At x equals negative 2, f has a local minimum because f prime changes from negative to positive at that point. At x equals 0, f has neither a local minimum nor a local maximum because f prime does not change sign. And at x equals 2, f has a local maximum because f prime changes from positive to negative at x equals 2. Number 20 is increasing on the following three closed intervals, from 0 to 1, from 3 to 4, and from 5 to 6, because f prime is greater than 0 on the open interval from 0 to 1, the open interval from 3 to 4, and the open interval from 5 to 6. F is decreasing on the closed interval from 1 to 3 and on the closed interval from 4 to 5, because f prime is less than 0 on the open interval from 1 to 3 and the open interval from 4 to 5. At x equals 1, f has a local maximum because f prime changes from positive to negative. At x equals 3, we have a local minimum because f prime changes from negative to positive. At x equals 4, we have a local maximum because f prime changes from positive to negative. And at x equals 5, we have a local minimum because f prime changes from negative to positive. Number 21, the function is increasing on the interval from 0 to 3, and that's the closed interval from 0 to 3, because f prime is greater than 0 on the open interval from 0 to 1, the open interval from 1 to 2, and the open interval from 2 to 3. F is decreasing never. For our critical points, at x equals 1, we have neither a local minimum nor a local maximum because f prime does not change sign. And at x equals 2, we have neither because f prime does not change sign. All right, so questions about any of that? Yes, sir?
Number 16.
16, okay. Well, first of all, we need to talk about what is the domain of that function. So, go ahead.
3, 2, close.
Okay. So the closed interval from negative 3 to 3 is the domain for that. Good. That's the first thing. So the domain is from negative 3 to 3. So we'll take the derivative, y prime, and we'll have to use the product rule. So it'll be x times 1/2 of 9 minus x squared to the negative 1/2 times 2x. Sorry, times negative 2x. So far, so good? Okay, plus 9 minus x squared to the 1/2 times 1. Still doing all right? Okay, so I'll do a little bit of canceling before I do anything else. I'll cancel out these 2's. And then I need to factor this. It's going to be a lot easier to find the zeros, especially if you're having to do this by hand, if you'll factor it first. And what we're going to do is we're going to factor out a 9 minus x squared to the negative 1/2 power because it has the lesser exponent. So then y prime will be equal to 9 minus x squared to the negative 1/2 times, I have x times negative x is negative x squared, plus, when I factor a 9 minus x squared to the negative 1/2 out of 9 minus x squared to the positive 1/2, I'm left with 9 minus x squared to the first power. So that's just plus 9 minus x squared. Make sure I haven't made any sign mistakes real quick. 16, 14, 15, 16. Yeah. So this is going to be 9 minus 2x squared over the square root of 9 minus x squared. and I want that to be set equal to 0. So that means the numerator has to be 0. So 9 minus 2x squared equals 0. So 9 is equal to 2x squared. So 3 over the square root of 2 is x, both the positive and the negative square root. Okay, do you need me to go on from there, or was that where the problem was?
Yeah, that's a problem.
The hard part for most people is factoring out this 9 minus x squared to the negative 1/2 power.
Yeah, I forgot times negative 2x.
Oh, yeah, not doing the chain rule would wreck this problem. Any others that you have questions about?
Number 15.
15, okay. Okay, there's a problem right from the get-go on number 15. Hang on a second. And that is that this function doesn't exist at x equals 0. So you need to think about that at the very beginning. X can't be equal to 0. There's a break in the graph at that point of some kind or another because this function is not defined at 0. So you start off by taking the derivative?
Yeah.
So that's going to be x times e to the 1 over x times negative x to the negative 2 plus e to the 1 over x times 1. I would factor out an e to the 1 over x. And we're going to have what? Negative x to the negative 1 plus 1. So far, so good? So we're going to want that to be equal to 0. Well, that means either e to the 1 over x has to be 0, or negative 1 over x plus 1 has to be equal to 0. Well, this is never equal to 0. E to a power is never 0, so that's never going to happen. And this is going to be equal to 0 when x is equal to 1. Okay, now the tricky bit about this one is, so we're going to start here at negative 4. At 0, my function is not defined, so I can have a sign change there even though the derivative is not 0 there. And then at 1, and then at 2. So if I substitute something between negative 4 and 0 into this, the e to the 1 over x is always going to be positive, right? So I'm just going to ignore that. So if I substitute in, say, negative 3, that would be 1/3 plus 1, f prime greater than 0. If I substitute in 1/2, I'm going to have a negative 2 plus 1, f prime less than 0. Now if I substitute in 3/2 for x, that's going to be negative, what, 2/3 plus 1, that's positive. Okay, so I'm trying to remember what they asked on this. Was it just find the critical point and then tell whether it's a local maximum, local minimum, or neither? So the only critical point is x equals 1, and that's going to be a local minimum because f prime changes from negative to positive. And we know that it's a continuous function. But that was part of the setup for this. What went wrong on yours? I'm just curious.
I didn't take out the e to the 1 over x. so I just had
And you were like, I have no idea what to do with this.
Yeah.
When you have more than one term, unless it's a polynomial, try and factor something out of it to make it nicer. Anything else? Okay. Then let me give you today's notes. And so I don't forget, I'm going to go ahead and give you your worksheet also. Because I'm really bad about it. Because we don't have a lot of worksheets in this class, I forget to give them to you. All right. So concavity refers to the way that a graph bends. I think we've mentioned this before in class. We talked about this is what concave up looks like, and this is what concave down looks like. And that's just graphically what it looks like. That's not really a definition. So notice something here. If I was to draw tangent lines, say on this graph, what kind of a slope does that tangent line have?
Negative.
A negative. And then here,
Positive.
positive. And then over here,
Positive.
a positive that is what related to this one?
Larger.
Larger. So the slopes are increasing. So when the slopes are increasing all the time, you have a function that is concave up. Notice also when something is concave up, and this comes up occasionally, and we don't talk about it very much, but it's an important thing to know, is that when something is concave up, the tangent line, except for the point of tangency, will be beneath the graph. Okay? As opposed to when something's concave down, if we draw in the tangent lines, let's say we draw in one over here, what's happening to the slopes over here?
They're decreasing.
Yeah, they're decreasing. And all the tangent lines are above the curve. Okay? So here my tangent lines are all below the curve and the slopes are all increasing. Now, what is another name for the slope of the tangent line?
Derivative.
The derivative. So the derivatives are increasing when something is concave up, and the derivatives are decreasing when something is concave down, and that's the way we define it. It has nothing to do with anything else. We're going to learn something else about it that's going to cause you to tend to forget this, but this is the definition. If the derivative is increasing on the open interval from A to B, then f is concave up on that same open interval. This is not a closed interval. And then conversely, if f prime is decreasing on the open interval from A to B, then f is concave down on the open interval from A to B. Now, we're looking to see if f prime is increasing or f prime is decreasing. Well, just think about any function. If you want to see where a function is increasing or where it's decreasing, we look at its derivative, right? If the derivative is positive, the function is increasing. If the derivative is negative on some interval, then the function is decreasing. So how can we look for where f prime is increasing?
Look at the derivative sign.
If I want to know where f prime is increasing,
Oh,
Look at
the
the
second
side.
derivative.
we look at the second derivative. And unfortunately, what happens is students start saying the second derivative tells you the concavity, and it does, but it's not the definition. The definition of concave up is an interval on which the first derivative is increasing. The definition of concave down is an interval where the first derivative is decreasing. And the way we check that is by taking the second derivative. So, assume that the second derivative exists for all x on an open interval from a to b. If f double prime is greater than 0 for all x on AB, then f is concave up. Why? Because if f double prime is greater than 0, and I want you to try and write that in tiny writing, so f prime is increasing, by definition then, f is concave up. And if f double prime is less than 0 for all x on AB, so f prime is decreasing, f is concave down. Again, the reason that the second derivative tells you about the concavity is because it tells you whether f prime is increasing or decreasing. Now, a point P that has coordinates C, f of C, and I put an extra word in here that doesn't makes this sentence make no sense at all. Kill the is in that first line. Oh, no, it does. Yeah, I worded this oddly. So if a point P where it's C, f of C is where the concavity of f changes from up to down or down to up, it's called a point of inflection. Points of inflection on a graph are really hard to see exactly where they happen. Two things that you can kind of look for though. One is if you trace over this, you left-handed? Okay, I think we've got all righties in here. If you're right-handed, when you draw this, kind of lightly trace over it. You will feel a shift in the way that you draw at that point. So you're drawing along, and it's like you switch from an underhand motion to an overhand motion. Right? You kind of feel that? That's where the point of inflection happens. The other thing that happens is this is going to be the steepest point. And that really doesn't make sense. That's why, steepest point. What do you mean? Points aren't steep, but you get what I'm saying. The point where the tangent line is greatest, or if it's going the other way, the least, is where your point of inflection happens. And, usually your tangent lines are either above or below the graph. At the point of inflection, it actually does like this. That's not perfect, but it actually goes through. It's tangent on both sides, but the curve curves one way on one side and curves the other way on the other side. All right, so if we're looking for, as on this one, points of inflection and intervals of concavity for a polynomial function, so we'll take the derivative. That'll be 15x to the fourth minus 20x cubed. And then we want to see where the first derivative is increasing and where the first derivative is decreasing. So we'll take the derivative of the derivative. So that's 60x to the third minus 60x squared. As we have done before, we want to set that equal to 0. I'll factor out a 60x squared. So either the 60x squared is going to be equal to 0, or x minus 1 is equal to 0. You can get x is 0 or x is equal to 1. And we'll kind of do the same thing we did before. Here's 0, here's 1. If we pick a negative value for x and substitute it, and it's almost always easier to substitute it into the factored form than into the expanded form. So if I pick a negative number and substitute it into this, well, the 60x squared is always positive, right? Times a negative minus 1 is still negative. So here, f double prime is going to be less than 0, which means that f prime is decreasing, which tells us what about f? What about f's concavity? Concave down. And the way we'll normally do that real quickly is do CC and a down arrow. If I pick a point between 0 and 1, say 1/2, well, the 60x squared is still positive. 1/2 minus 1 is negative. So f double prime still less than 0. So f prime is decreasing on that interval also. So f is concave down still. But if we pick a value larger than 1, 60x squared is still positive. Something bigger than 1 minus 1 is positive. So now the second derivative is positive. That means that f prime is increasing, which means that f is concave up. So f is concave up on the open interval from negative infinity to 0 and on the interval from 0 to 1. Oh, I'm sorry. Thank you.
Hey, yes, sir. You just got me. It's not the same song. It's got me.
And it's concave up on the interval from 1 to infinity. And because we have a change in concavity at a point that's defined on the graph, we say that f has a point of inflection, which is usually abbreviated POI, P-O-I, at x equals 1. Okay, it's not too bad. We're just drilling down another layer. So find the points of inflection of f of x equals x to the 5/3 power. Okay, so f prime of x will be 5/3 x to the 2/3 power. And f double prime of x will be 10/9 x to the negative 1/3. Well, notice this function is never equal to 0, is it? Because that's the cube root of x in the denominator. 10 over 9 cubed roots of x is never equal to 0. Sorry. Does that mean there are no inflection points?
Yes.
Not necessarily, because just like we do with the first derivative, our critical points of the original function were where the derivative either was 0 or didn't exist. Right. So f double prime is undefined at x is equal to 0. So it's possible that we could have a change in whether the first derivative was increasing or decreasing at 0. It's not a certainty, though. So if we substitute in a negative number into this, we get that f double prime is less than 0 because the cube root of a negative number is negative. That means that f prime is doing what? Decreasing, which means that f is concave down. And then here, if I substitute a positive number into the second derivative, I get that f double prime is greater than 0. So f prime, therefore, must be increasing. So f here is concave up. So f is concave down on the open interval from negative infinity to 0, and f is concave up on the open interval from 0 to infinity. And f has a point of inflection at x equals 0. I'm interested, just real quickly, grab a calculator. Let's see, what does x to the 5/3 look like? Turn off my plot. It's one thing about switching back and forth between stat and calculus.
This looks like pretty standard. Pretty standard graph.
Yep. Up.
It's gonna woo.
Up.
Looks like x to the third. I mean,
No.
x to the.
You mean the cube root of x?
I don't know.
Good shape.
Well, let's compare this to x to the 3rd power.
X, yeah, x cubed. That's what I meant. Yeah, it's just a little wider. It's a little thick.
It's a good shape.
It's a big chair.
It's a long shape.
It's an ergonomic chair. Lance would say.
Yeah, notice that both of them actually flatten out at 0. I'm going to turn my x cubed off. Actually, I'm curious, what if we did x to the 1/3?
Oh, it's super wide, and it's also flattened. Does not flatten out. It's not nice.
Oh. It's not fun. It's like
It's kind of weird.
It's like,
Yeah, instead of
woo.
what about x to the 2/3? I'm gonna do all of these.
X to the 2/3 looks like a seagull drawn by a 5-year-old.
And we're gonna do x to the 4/3 too. Yeah, I don't think that one. Ooh, 4/3 is like pointy parabola.
A pointy parabola. Is there such a thing as a pointy parabola?
Oh yeah. Graph x to the 4/3 and you'll find out.
All right, well, let me zoom in on this one a little bit. So it does kind of have a little flat spot right there. And you said to the 4/3 is the one that's funky?
It's a pointy parabola, not a curvy parabola.
Pointy parabola.
Yes.
We'll have to zoom out to see it. Oh, interesting.
Why?
Well, if you think about it, if y was equal to x to the 4/3, then its derivative, y prime, would be 4/3 x to the 1/3. The derivative will be 0 at 0. So if you zoomed in enough, it should have a little bitty flat spot there, because the derivative is 0 at that point. At 0, rather. See how if you zoom in some more, it becomes, you can kind of begin to see that it's going to be flat on bottom. But it's not flat for very long. All right. Sorry, I was just interested in what that looked like. So if you think about this for a second, inflection points of f occur where f prime has either a local maximum or a local minimum. Because at that point, f prime is going to change either from increasing to decreasing or decreasing to increasing. So one of the things that you can be asked is, given the graph of the derivative, you can be asked about where the original function has points of inflection. And occasionally, this is a really good question, because students who just know, the second derivative rule for finding these are like, oh, I need to figure out what the second derivative looks like, and it takes them forever. Whereas for the rest of us, we just go here, here, and there. X equals 1, x equals 3, x equals 5. Because where f prime is increasing, f is concave up. Then here, where f prime is decreasing, f is concave down. Okay, and it can get confusing. You have to be careful. You have to be thinking clearly. I'm thinking about concavity, or I'm thinking about whether the function is increasing or decreasing. Okay? All right. The second derivative test. We have a first derivative test to find local maximums and local minimums. We also have a second derivative test to find local maximums and local minimums. You may be asking, why in the world would you take the second derivative? Well, there are times when we know the value of the second derivative, but we don't know what the second derivative function actually is. I've given you one that's a polynomial, but you're more likely on the AP exam to get something a little more complicated. So here's the deal. Let C be a critical point. That means either the first derivative is 0 or the first derivative does not exist. If the second derivative does exist, oh, wait a minute. If the second derivative at that point exists, does that mean that the first derivative couldn't exist? Can you have a point where the first derivative doesn't exist, but the second derivative does exist?
Yes. Wait. Oh, no, I thought you said it the other way around. I thought you said where the second derivative doesn't exist, but the first does.
Yes, you can have that, but if the first derivative doesn't exist, You have a function where the point doesn't exist, you can't find the derivative of that function because that function was discontinuous.
Yes.
So when it says critical point, you're like, oh, that means f prime's got to be equal to 0. Then if f double prime of c is greater than 0, then f of c is a local minimum. Because if f double prime is greater than 0, that means that you must have had something that was concave up. Your critical point will be where the derivative was 0, so that's going to be a local minimum. On the other hand, if f double prime is less than 0, then at that point you're going to have a local maximum. And it feels a little bit weird at first because you're like, oh wait, the second derivative is positive, so I have a local minimum. It feels strange. Okay? And if the second derivative is 0, then this test fails to tell you anything important. So let's use this to analyze the critical points of this function. F prime of x is 3x squared minus 12. I'll set that equal to 0. I think you can probably do that in your head. X is plus or minus 2. I could do a number line and look at how the sign changes to find where I've got maximums and minimums. But I could also do this. Take the second derivative. That's 6x. F double prime of 2 is 12. That's greater than 0. Therefore, f of 2 is a local minimum. And f double prime at negative 2 is negative 12. That's negative. Therefore, f of negative 2 is a local maximum. So when will you use that? Well, if the second derivative is really easy to take and to evaluate, sometimes it's better. The other time is, frankly, when you're going to be told the first derivative is 0 and the second derivative is negative 3. What happens? Well, that means the original function must have had a relative maximum or a local maximum. Okay? All right. That is it for today's lesson.